Hello and welcome back. In this tutorial, we will show you how you can use the software to design stable control loops. PI Expert offers several feedback options, but the two most important options are the secondary side feedback using simple Zener reference and the secondary side feedback with an error amplifier like the TL431 shunt regulator IC. This is a top switch HX based design with a 5-volt 4-amp output. Clicking the feedback block from the block diagram view or clicking on the components link under the feedback option from the navigation tree open the feedback dialog. This particular design uses the TL431 option. Just a quick mention here that you can also change the feedback type to say a secondary Zener feedback through the feedback bias dialog. Select the feedback type from one of the options here. Let's leave the default selection for this example. Let's navigate back to the feedback components dialog. As you can see, a detailed feedback loop circuit is suggested along with recommended values for the components. These values are calculated such that the crossover frequency is achieved at a minimum phase margin of 45 degrees. In this example, we have an estimated phase margin of 87 degrees. I have another example which I will quickly open up here. In this example, which is a 12-volt 3-ampere design, the software recommends a slightly modified feedback scheme which makes use of the phase boost network in order to achieve the minimum 45-degree phase margin. In absence of the phase boost network, you can see that the estimated phase margin is only 33 degrees. Clicking on the chart button opens up a Bode plot showing gain and phase plots against frequency. This chart gives a better feel for the overall loop performance rather than going on values of crossover frequency and phase margin alone. After all, loop stability is all about the shape of the Bode plots. Let's go back for a second and review some of the feedback elements and what role they play in the stability of the closed loop. The main compensation elements are RF2 and CF1, which form a 0 at the low frequency, typically for HX designs around 100 Hz. Additionally, another compensation pole is derived inside the top switch and is located around 7 kHz. This pole also serves as a noise filter for the controller within the top switch. This pole-0 pair forms the basis for the phase compensation of the loop. The gain of the loop can be adjusted by varying resistor RF3. The phase boost network is a RC network placed across RF3, and it boosts the phase around the crossover frequency if it is required. When you optimize a design, the software automatically makes initial calculations based on the primary inductance and filter capacitor values, and then it presents you with a recommended circuit for a first prototype. One final word before we conclude this tutorial. Please choose the crossover frequency wisely. It is a common misconception that higher crossover frequency or higher bandwidth is always better. This is incorrect. Too high a bandwidth means a hyperactive control loop, which then reacts to very high frequency noise injections. I always recommend to try and limit loop bandwidth below 3 to 4 kHz at most for top switch based applications. For DPA switch, the loop bandwidth can be a little higher, around 8 to 10 kHz, due to the higher switching frequency of this part. We do hope that this tutorial has been helpful to you and that the software can assist you in designing stable loops. Thanks and good luck.